In this tutorial, we're going to explore the use of the F block in SimSmith. The F block allows the user to type an equation which SimSmith evaluates to compute a new impedance. It takes an equation which takes this as the input and computes this as the output. Equations can include the familiar add, subtract, multiply, and divide used in virtually every programming language. These operators are sufficient for most purposes, but can be inconvenient. Specifically, to compute the impedance of two parallel resistors, one would have to write this. Notice that this equation is the 30 ohm resistor. This is a cumbersome mechanism for such a common operation, and consequently, SimSmith provides a shortcut. In particular, it provides the parallel operator, which is a vertical bar, which makes it much easier to type. SimSmith function equations have some other special operators and variables which make writing the equations easier. We've already seen one variable, the I variable, which is the impedance of the circuit on the left-hand side of the function block. Let's introduce two new operators, the J operator and the W operator. The J operator indicates that the following number is a reactance. For example, would mean a 50 ohm resistance and a plus 10 ohm reactance. The W operator is just a convenient form of omega, which is to say the operating frequency specified by the generator multiplied by 2 pi. The omega, or W, is not a number, it is an operator. It must be followed by a number. As we shall see, making the W an operator simplifies expressions. Let's try some equations. Suppose we want a function block which introduces a shunt capacitor of 300 puff. I in parallel with, now we know from circuit theory that the impedance of a capacitor is 1 divided by J omega, we said 300 puff. Notice that J and W are both operators with a higher precedence than division. This means that it will compute J omega 300p before doing the division. Even typing this much is a little cumbersome, so SimSmith provides the C operator, and we can write C 300p instead of 1 over J omega 300p. SimSmith ignores all white space, so we can write this equation in a somewhat more readable form, which I've already done. There are times when we want to adjust the value of a capacitor, and we can do this by using a variable. Let's say 300p here, and we can retype this equation as CA. And this allows us to modify the value of the capacitor. Now, these circuits are easily realized using traditional Smith chart elements. The real power of the F block is in providing functions not normally available. Consider a simple diplexer. A diplexer is a circuit which provides a constant impedance but passes only certain frequencies on to the load. Let's consider a low-pass diplexer. It would start with a series L and a shunt C. Now, here we're looking at the SWR, and we see that at very low frequencies, the impedance has an SWR of 1, which would mean that the impedance coming in would be 51 ohms. At higher frequencies, though, we see the impedance in is way off of the 50 ohms. And this is because at higher frequencies, this capacitor becomes a short circuit. What we need is a capacitor in series with a resistor, and the function block can provide this. Now, the capacitor had a value of 318 puff. The resistor had a value of 50 ohms. And the equation that we wanted is I in parallel with CA plus RB. Now, as we saw in earlier tutorials, the R is really redundant, but we leave it there just to make things a little more readable. Once we have this resistor in place, we notice that the input impedance for all frequencies is 50 ohms. We see that because it's got an SWR of 1 all the way across. Now let's look at the power into the circuit. Here we see the power in. At low frequencies, SmithTutorial says to deliver 1 watt, we need to provide 1 watt into the input. At higher frequencies, we see that in order to deliver 1 watt, the generator would have to deliver 9 watts or even 10 watts. And so we see that at high frequencies, most of the power in is going to the resistor inside the function block. Let's go back and consider some more properties of the F block. One really useful feature of the F block is in seeking a combination of values. Suppose we want to build an LC notch filter which is resonant at 10 megahertz. There are, of course, an infinite number of LC combinations which will resonate at 10 megahertz. We want to be able to adjust the C and have the L adjusted for us. I've already done this design. Let me go ahead and load it in. Here we see a plot of the SWR, and we see that at low frequencies, which the notch filter should let through, the SWR is fairly low. We notice that at high frequencies, again, the notch filter should let these through, and the SWR is fairly low. But at 10 megahertz, we find that the SWR is very high. Here it shows 14 milliohms, which means that the impedance looking into this looks like a short circuit. Let's look at the equation. The equation is the input in parallel with an L, whose value I compute right here, in series with a capacitor. We can play with the shape of this somewhat by playing with the capacitor. We can make it more narrow by making the capacitor smaller. Make it wider by making the capacitor bigger. Notice that the frequency is not moving. I can move the frequency. And so SmithTutorial has now allowed me to play with 2 variables and compute the third automatically. Let's look at another example of using this ability to compute one value based on another. This example is the common J-pole end-fed half-wave dipole. Half-wave end-fed dipoles have very high impedances, often above 4,000 ohms. In order to match this high impedance to a 50 ohm feed, the J-pole uses what is called a resonant transmission line transformer. This type of impedance match is often confused with a quarter wave matching section, but it is a distinctly different circuit. Like the quarter wave matching section, the resonant feed line transformer is 1/4 wave long. However, unlike the quarter wave matching section, There is no magic impedance value for the quarter wave section. A 50 ohm coax can be used to transform the high impedances down to 50 ohms. This is what the circuit looks like. We have an antenna, a 1/4 wave resonant feed line. Here's our transceiver, and we can adjust the input impedance by moving this tap point up and down. I've already done this design as well. Let's take a look at the equation. As we saw in the circuit, it's two parallel transmission lines. One is a shorted section down at the bottom, which has length A. The other is a section which has I, the antenna as an input, has length B minus A, and again I just used a variable D for the impedances. As you can see, we've managed to match this very high impedance over here down to about 50 ohms, pretty darn close. And even if I change this substantially, moving this allows me to pre-perform the match. Again, we're using the F block to provide a calculation which makes sure that the two transmission line sections together have a total length of 24.59 feet, but I can make the trade-off of how long each one is. Well, this pretty much finishes up our discussion of the F block in SimSmith. For a complete description of the F block expression syntax, please see my webpage. In this tutorial, we've explored the use of the function block in SimSmith. We saw the F block can be used to model circuit elements not commonly found in SmithChart software. Also, we've seen that the F block allows us to tune more than one parameter at a time using a single variable. Future tutorials will deal with the specific applications of the SmithChart in general and introduce new features of SimSmith as they become available. Please feel free to contact me with any suggestions for features or to report any bugs. 73 and best DX.